It is often said that the largest engineering systems in the world are the power grids. The power grids in every country. Now, if this is not obvious, it's mainly because they're so distributed. And being so large engineering systems and so complex engineering systems, it means that they will not be replaced from one day to another. So when we talk about a smart grid, we're not talking about a completely new type of system. So it's not like having a watch and then a smartwatch, where the smartwatch is completely different to a watch. The smart grid is effectively an evolution. So it is an evolution of the power grid where we have the use of sensors, the use of communications, the use of computational ability and control in some form so as to enhance the overall functionality of the electric power delivery system. So it's a very natural evolution in a sense. It's the very natural next step in the power grid rather than a completely new type. Its aim in general is situational awareness. So what we get with the smart grid is that we have better accuracy, perhaps, better accuracy in evaluating, in monitoring the demands, in identifying outages. In this sense, we have better response. Of course, if we have better accuracy in this, we can have better prediction. And all of these also help in more effectively incorporating renewable energy sources, because for renewable energy sources we need to have some accuracy regarding the demand at any point in time, because the wind will blow when the wind will blow. It's not like we can expect when the wind will blow. In this sense, we cannot predict accurately the solar energy that we will have in the next month. It's not possible. We can have some prediction, but not an accurate prediction by any means. So having a better understanding of the changing demands and a better understanding in general of the state of the power grid helps with response and also with incorporating energy sources. But there are more advantages, mainly financial, I would say, but not only. Now let's see an example of how a smart grid might look like. Now, I emphasize on this being an example because there is no such thing as a blueprint as to how a smart grid should look like, but it is sufficiently vague, I must admit, so that it should represent quite a few different types of smart grids. But let's say this one. So on the left side, there is the power generation with the fossil fuel power stations on the top, nuclear power stations, also wind turbines, solar farms, other different types of renewable sources of energy, and any other type of sources of energy, and the transmission lines through which the energy is transmitted and later distributed to the residences on the right, the power consumption side, the right side, the businesses, the different factories, plants, all the different users of electricity. In the middle, the power transmission and distribution has the substations, and on the network, this is where we see the PMUs. So the PMUs, a few more. This is phasor measurement units, and these are effectively what we might refer to as the sensors of the whole system. So these are effectively the systems that monitor its health. So they monitor the voltage, they monitor the current, generally they try to detect if there is any risk of outage. They are the sensors of the system in general. And there are also the PDCs, the phasor data concentrators, which aggregate data from PMUs and report them here to a control center. So from the PDCs, so I'll write here PDC, so the PDCs are somewhere in there, and they aggregate data from multiple PMUs, and then they send them to the control center of the power grid, so that the power grid will have the power grid operators will have a good understanding, a good situational awareness of the state of the grid. And why is that important? Why is a good situational awareness is important? Well, it is important because what people might be using on the right side, so what the different households and the different businesses and everyone might be using on the right side in terms of energy, it can be volatile. There is generally an expectation that it might look like this. So let me draw an expectation at best. So this is the load, normally in megawatts. And this is the time of the day. So this is midnight to the other midnight. Let's say 23:59. And when we go to bed, it is pretty low, the load. Might look like this. Then when we gradually wake up, it goes up, and then it will be up for the whole of the day. and then gradually going down when we go to bed. So this is an expectation, but of course it might be many cases when it doesn't look like this, and instead there might be, let's do it there. There might be some kind of spikes for no reason in different, okay, not for no reason, for unexpected reasons in other times. So when we have such spikes, well, situational awareness then is very important, because what will happen what happens when the response, which effectively is the generation of power, if power generation does not meet power demand, then this is when we have outages. Then this is when the power grid goes out of sync, and we have even blackouts. So it's very important to have good situational awareness. It is also good for financial reasons, because for these peaks in time, this is when the energy is not cost effective. This is when the power generation comes from the expensive sources of energy rather than the cheaper sources of energy. To increase this situational awareness across the world, there have been multiple programs for introducing smart meters everywhere. So in most of the Western world, the smart meters are everywhere now, but across the whole of the world, generally, smart meters would be expected to be installed. So the logic of a smart meter is that it charges what actually happens. So it charges for the true amount of electricity that was used, while up to recently, before the smart meters, the measurement was mainly based on estimation. Perhaps then adjusted for reality after measuring it after a few months, but at the real time it was estimation. Now at near real time we can have the true value being transmitted to the operator, to the power grid operators, to the utilities. This means that if we have the true value, so the expected, the actual value rather than the estimated value for the electricity that is consumed, we also have a very good source of data for predicting what will happen in the next 15 minutes, in the next hour, in the next few hours, rather than guessing based on historical data. So this means that there can be better balance between supply and demand, and this has two advantages. Better balance between supply and demand means that it minimizes the risk for any blackout, for going out of balance, for going out of sync. But at the same time, it is more cost effective. So the power generation will happen in the way needed. So there will not be more power generated than needed, which will be a waste of money to a large extent, or there will not be less power than needed, in which case there will be an outage. And another important characteristic of our smart meters is that they can both send and receive data. So not only they send the amount of electricity that it was consumed to the utility, but they can also receive data from the utility. So for example, when they can receive updates, but when the value changes for electricity, then this shows the change in the actual cost. How much we will pay at home, for example, will be shown on the meter. And this is one of the reasons why there is both send and receive functionality on a smart meter. But there is also another reason for having this send and response functionality in general, not just smart meters, but in general in the concept of the smart grid. Now this is because we can cope better with demand during peak times if there is any way for any kind of interaction between the generator and the user, between the generation and the user of electricity. So, for example, if we go back to the situation where we might have a peak, whether predictable or not does not matter, of load at some point in the day, and as we said, if it goes over some kind of threshold perhaps, or if it is generally in the peak, then it is expensive to generate energy, so it is expensive also for the customer, of course. Then one way to address this is by having what we call demand response. So in the power grid in general, demand response can be extremely low tech. It can be the utility calling a few plant managers and letting them know that it might be a good idea not to use a lot of energy at this point in time because it is very expensive, but instead it might give them incentives, even financial incentives effectively, so that they don't use most of the energy at this point in time, but they use it, let's say, later, so that then this peak will disappear and the power grid can cope. So it might look like this, for example, rather than, or perhaps like this, rather than having a single peak here. So for this to be achieved, there's this kind of demand response, there's kind of this interaction, and as I said, it can be very low tech, it can be just a phone call. But with the smart grid, when we have increased automation and increased networking, then it can be fully automated. So it is possible to have the systems, of course, with collaboration with the plant managers, systems in a factory, in a plant, that are switched on or off. So they might not be used or might be used during different times of the day, depending on the cost. So it might be when this is now cheaper in real time, not because we have some kind of plan that says that specifies that perhaps from 3 o'clock to 5 o'clock it is cheaper, but because in real time it happens to be cheaper. So it's not a long-term plan, it's a real-time daily dynamic update and a different situation, a dynamic situation effectively that it is possible to monitor, it is possible to control if there is a smart grid rather than a traditional power grid without these abilities to communicate the sensor data, take decisions in real time, and have a send and response, a send and receive functionality between an interaction between the utility and the user. Of course, actually, before we go to the next one, of course, this can be exploited. So if we think about how a hacker or generally a cybersecurity breach might affect this, the power grid, thanks to the demand response. Well, demand response uses, let's have it drawing. So this is the generation. Actually, no, not the generation. Let's go for, this is the use of energy on this side, or the user of energy. And on the other side, we have the utility. Now, if the user of energy is sending information to the utility, then we can, or a cybersecurity breach can lead to grabbing this information from here and knowing what people do. But then again, there's not just this. There's also the ability to receive data from the utility. Now, let's assume that someone pretends to be the utility. So we have here someone with, let's imagine that this is a black hat, although I'm using a red pen in this case. So a black hat attacker is hijacking this communication and is sending information to the user of energy as if they are the utility. Now, in this case, they can send some kind of a command, such as shut down the system, because this is what the demand response system may have specified for the specific energy and utility pair. And if someone takes control of this process of providing the responses, someone takes control of the process of creating commands from the utility to the user of energy, then there is the possibility of affecting actuation on the side of the user. Well, so this is sensor data that is sent to the utility, but it is actuation commands that are sent from the utility to the user of energy, in addition to information and any other kind of data, of course. And in a smart grid, perhaps generally in a power grid, but certainly in a smart grid, communication delay is extremely important. Generally timing is extremely important. It's more important than in most other industrial control environments that I can think of. So the IEEE and the IEC have in fact specified requirements, very strict requirements for communication delay. If it's communication inside a substation, then for protective action, the delay should not be higher than 4 milliseconds. So by protective action, I would mean something critical like opening a circuit breaker to prevent damage from high voltage. So these kinds of critical actions, protective actions. If it is external, if received externally, then it should not be over 12 milliseconds. Now, I'm not entirely certain if these numbers have changed. These are the numbers I remember when originally they were set. What matters is that they are very low. These are very strict requirements. So we don't see such requirements for network communication for anything else, really. Perhaps for the critical, for the high-speed CAN bus and FlexRay inside the car, for the critical functionalities of a car. But for most other things, 4 milliseconds and 12 milliseconds these are very low thresholds. So, or these are very low limits. So they can be exploited, of course. By being very low, it means that they can be exploited. An attacker would not affect the confidentiality, wouldn't matter that much in relation to communication delay. Perhaps not the integrity, but would go for the availability. So if one delays communication, if one has uses some form of denial of service attack if they have connected to the network, or perhaps a jamming attack, if there is wireless communication involved, then this delay will go over the 4 milliseconds and the 12 milliseconds respectively, or significantly over these limits, and this means that it will start affecting the integrity of the protective action. So it will start delaying the very important actuation that needs to happen when protective action is needed. So opening the circuit breaker to prevent damage from high voltage. If that happens too late, then the power grid might fall out of sync, and then we might have an outage. So the communication delay plays a significant, perhaps very significant, very important role in the smart grid. And in fact, for this timing, generally timing plays a very important role. And in fact, the type of system that is used by PMUs, by those phasor measurement units, the sensors of the smart grid, and any other grid devices, the measurements of time are based on GPS. Now, most people consider GPS, and of course it is, as the primary mechanism for finding one's location, for navigation and so on, in outdoor environments at least. But in practice, the GPS is also very useful, and this is what it is used for also in the finance sector. It is very useful for providing accurate timing, accurate measurements of time. That's because it carries the most accurate clocks in the world, atomic clocks, inside its GPS satellite. So its GPS satellite will have an atomic clock inside, and this atomic clock is there so as to have a very accurate synchronization between the GPS systems, between the user of GPS and the GPS satellite. And for this reason, it means that everyone can use it also to have very accurate time measurements. So when we have something as distributed over very large areas as is the smart grid or the power grid, then the GPS can offer the exact time, as exact as possible, of course, to the different distributed, the very different geographically areas of the power grid. If we have accurate measurement, then we can have accurate identification of errors. Then it is much easier to detect if there is any issue in the power grid if we have correct synchronization between the different users. So what it does is that it provides time stamping that is precise for the measurements, but also for the actuation command. So it is useful for both for the sensing perspective, but also from the actuation perspective and the forensic perspective. When something has went wrong, or not really forensic, from the maintenance and repair perspective. If something has gone wrong, where is it? And this depends on the time, because we can detect where an error, where a problem has occurred in a large system like the power grid. Where exactly on the line, or approximately on the line, it has occurred based on the time. So the time an error times to propagate through the distribution lines, through the transmission lines, this is determined based on time. This is what helps us detect where it is in terms of actual geographical location. So time plays a very important role. But how can we affect then this time? Well, by affecting the GPS signal. Or since the GPS signal itself cannot be affected, by faking it, by creating a spoofed GPS signal, or by jamming the GPS signal so that the GPS signal is not received by the user, by the power grid components in this case. And if that happens, then the timing will not be correct, and this will affect the time stamping of the measurements and the commands and so on. I've mentioned also there meaconing. Meaconing is the type of spoofing which is based mainly on delaying a message, so capturing and sending it later, rather than creating a brand new fake message. So it's a version of spoofing, meaconing. In terms of cybersecurity, I think it's better to finish with what makes the most difference in terms of the cybersecurity of the smart grid, which is a smart meter. Unlike the meters that we used to have, which would effectively provide the data for our energy usage every, let's say, 1 month or 3 months or more, then the smart meter does this every 15 minutes, every 30 minutes. So there is a massive difference in how real-time, how recent the information is, how real-time the information can be transmitted to the utility. So that means that if one grabs this kind of data, let's say intercepts it while it is transmitted by the smart meter to the utility, then this creates privacy issues. So one can tell, for example, when people are at home. If there is a spike in the energy, then we know that they used some device perhaps. Or if there is less energy usage than normal, then perhaps they are not there. So we can tell whether there is anyone at home, how many there are, perhaps even the sleeping or waking up patterns, which is very important, of course, in terms of security. But there is also the potential of integrity attacks. So, for example, false data injection by physically tampering with the devices so as to extract the secret keys, and then use a laptop to pretend to be a smart meter and then report false data to the utility. Or if there are many of these, then report this false data at great scale, at massive scale, and in this way create a false impression to the grid that there is less or more usage of energy in this area. And of course the grid will have to respond accordingly, so either increase or reduce the energy that is transmitted in this area, which of course would be based on wrong data, and as a result would lead to a lack of synchronization, hence some form of outage, even a blackout.